meatballs, lingonberries? Boy. I confess, it's always the backup choice on the lunch menu at the museum where I work, and I end up picking it about 2 days a week. Which should tell you something about the food at the Boston Museum. Eric, do you have any announcements we need to make? Everything's running smoothly, a well-oiled machine. Thank you very much. And our next speaker this afternoon is Dr. Alf Brubakk, who's Professor of Environmental Physiology on the Medical Faculty at the University of Trondheim in Norway. And he works with all sorts of problems dealing with the effects of the environment on the human body. He's specialized in what's relevant for us in decompression effects, gas effects on the human body. Starting out originally from the idea of using ultrasound to measure bubbles, which as he explained to me, he thought was a nice simple problem to solve 25 years ago. And he will talk about, can decompression sickness be prevented? Dr. Brubakk.
Thank you for inviting me. The answer to the question, of course, is yes and no, as I'll try to show you. I feel somewhat like this guy, trying to address you because when I'm listening to the kind of diving, I dive myself, but on a totally different level. I understand that it's totally different levels of maturity. But still, we have the same problem. We have to get home again. And already in 1847, authors commented that the problem is to get home. And it was commented on here that you have to realize that the dive isn't over until 24 hours after you come out of the water, which is very, very true. And I'm going to tell you some things that hopefully is useful about how to get home. Why do we do research at all in this field? Well, the aim of this is to develop a procedure that reduces the risk of injury to the central nervous system. And I particularly underline or mark that because I think that that is the real critical thing, as I'll discuss a little later. But I think that it is the central nervous system, it's the problems related to that we have to prevent. And other symptoms or other undesired effects of decompression will not be mentioned much in this. So we can do that in two ways. We can either develop the methods to reduce bubble formation, as the bubbles is the basis for the decompression problems, and we can reduce the effect of these bubbles on the organism. And my basic tenet to prevent this is that we do that by understanding better the mechanisms that are related to this particular problem. I think there is a universal agreement on the fact that decompression sickness or decompression illness, as it's also called, is caused by gas phase separation and how the body reacts to that. So that is sort of the basic tenet, and I don't think there is much discussion about that particular fact, that is the basic problem that we're facing. And generally, most would say that if you have the sum of partial pressures of gases in the body exceeds the environmental pressure, then you can form bubbles. However, that is only partly true, because if you look at some of the data, the pressure gradients that are needed in order to produce bubbles, if you look at gas or inert gas in water, you'll see you need a very high supersaturation pressure in order to get gas phase separation. However, in tissue and in vessels, this gas phase separation requires much less. And even there are data indicating that very, very low levels of supersaturation, nearly any supersaturation that you have from saturation with air, for instance, at 3.5 meters is enough to produce significant amount of bubbles in the majority of the test subjects. So there is a discrepancy here, and we believe, most believe, that that is caused by something called bubble nuclei. And they are small gas-filled spheres that is present on all hydrophobic surfaces, probably, in tendons, fascia, parts of the endothelium. They are gas-filled, we believe, because you can crush them. So it's probably gas-filled, approximately 1 micrometers of diameter. They can have different size and shape. They will grow with increasing gas tension and decrease with local pressure. They will decay very slowly, perhaps by some mechanisms of diffusion limitation caused by the surface properties of this bubble, and the lowering of surface tension, will make larger bubbles stable. So they are, you understand, this is a dynamic process, and we frankly do not know why we have this gas nuclei. No one has shown why are they there. I mean, evolutionary, there is no particular reason why we should have gas nuclei, but they seem to be present. There seems to be enough indirect data to indicate that they actually are there. And the importance of that can be very easily shown in this particular experiments, which we did in a series of many, many experiments. And as was mentioned here at the beginning, my start in all this business was that I was working, and worked for many years before I started on this, in cardiology and anesthesiology with ultrasound, and I knew that bubbles were easily detected by ultrasound, and that's how I got interested in this particular problem. So if you measure then gas bubbles, as we can do, we can give them in absolute values in an experimental situation. And this is then a dive, it's performed. This is the amount of gas bubbles that are produced. Then this is part of a series where we tested different kinds of treatment regime. And you see that you give a treatment, and all the bubbles disappear. And when after the dive, there are no bubbles. Then you do a repeat dive, and you see that you get exactly as many bubbles as you get before. So that is sort of growth of bubbles from nuclei. However, if you do the same type of experiment, but a bit different outcome, you do a decompression dive, again you do this was a different treatment, but that's not important, and you see the gas phase that was detectable here was eliminated by this pressure peak, but after you come back to the surface again, you see there are still bubbles present. And then the second dive performed like that, you see there are much more bubbles present. There are lots more bubbles because this grows from bigger nuclei. And this is of course a very interesting question when you're also interested in repeat dives. Because repeat dives, if there are actually bubbles or bubble nuclei, larger bubble nuclei present at the second dive, this is what you'll see. Our main hypothesis is that serious decompression injury is mainly caused by the reaction of the body to intravascular bubbles. We have quite a lot of experimental evidence to indicate that that is actually true. And we also have shown that the venous bubbles activate the endothelium, leads to endothelial damage and activation. I'll come back to that in a moment. And that can lead to changes in endothelial function on the arterial side. Most of the bubbles are formed on the venous side, but on the arterial side, there also are changes or reduction in endothelial function without arterialization of bubbles that we can see. We can't, bubbles that are below a diameter of something like 15 to 20 microns are probably not detectable with our techniques, but still, we have an effect on the endothelium on the arterial side. And the so-called tissue bubbles, they're only important for the dynamics, gas uptake and elimination. It has no really important pathophysiological meaning when it comes to serious decompression sickness. And this is the endothelium of a pulmonary artery, and the normal pulmonary artery. If you give bubbles, this is what you'll see. Areas where this layer, the surface layer is gone, and this is the muscle layer underneath. So this is the series, and we are sort of having a global approach to this problem. And I've said here, dense is a red herring, in the sense that it is such symptoms are so dramatic that most people have focused, and that is the problem. I don't believe that. We don't believe that. We believe that the real problem is the effect on the central nervous system, and that has nothing to do with having pains in the shoulder. That can be related, I'm not saying that, but that's not the main pathophysiological problem in our approach to this problem. And the reason we have chosen this way is to use something called Occam's razor, which says that you should always, from a set of otherwise equivalent models, use the simplest one. That's the Occam's razor. That makes it easy to take away things that we don't think is important. You can challenge me and say, okay, we think there are data. We believe, that's what most people say. We believe that tissue bubbles are of importance. And I say, okay, show me the experimental data, and we can discuss that. If you don't have anything, belief has nothing to do in this business. It has something to it. It's a lot to do, really, but not very important. This is from a series of experiments that we did in order to demonstrate the effect of gas bubbles. You see here, this is the grading, grade 1 to 2. As you know, the grading of ultrasonic, the higher the grades, the more bubbles there are, generally. Grade 1 to 2, there are very few bubbles. This is quite a lot of bubbles. This is a study that we did in animals. And on the x-axis here, this is the function of the endothelium. And the function of the endothelium is measured 100%, or high percentage means that you have a good function. You see here our controls. The controls. Then the one with the low, after 1 hour, you see there are no effects on the endothelium at all. But then, if you have the serious, a lot of gas bubbles, you see there are a measurable reduction in function. However, if you have few gas bubbles, you see that even after 6 hours, you have an effect. You have a delayed effect. So the endothelium is even at very low levels of bubble production, the endothelium is affected. Now, this is from one study, but there are many, many other studies showing general, if there is an opening between the right side of the heart and the left side of the heart, the risk of decompression problems is higher. So-called patent foramen ovale, which about 30% of us have, if you have a, but only 6-7% has a big one. The risk of decompression problems is increased, and the risk also of brain. This is not quite correct because there are not ischemic lesions, but there are measurable. You can find changes in the central nervous system. The risk is also higher if you have a patent foramen ovale. So if gas has an easy way to pass into the arterial circulation, the risk of serious injury is higher. And these nuclei are on the sticking to the endothelial lining of the vascular system. Was already argued in '52 by Harvey, who did a number of studies of that. So the point is, and the bubbles stick to this surface until they reach what he called the point of instability. And that was sort of the starting point for our studies, where we believe that, yes, the same model, the gas bubbles form at particular places on the inside of the blood vessels, on the endothelium, and then when they reach a certain size, they dislodge and come out into the bloodstream. And in order to study that, we combined two experimental models. We have a diving model, and this is by one of my co-workers, who, when he heard about the crazy things that we did, and then the rat, the exercise model in the rat. And what we actually did was that we have an exercise model where we exercise rats in the same way as you exercise top athletes, or that you should do if you want to really get fit, is that we do interval exercise with very high intensities, 85 to 90% of VO2 max, and you do that over a period. In this particular experimental setup, we use 90 minutes. We exercise them 5 days a week, and our idea was that we wanted to show, we thought that if you're in better physical shape, if you have higher aerobic capacity, your risk of bubble formation would be lower. We had some data indicating that was so. We were wrong, but that was a different story. Because what we found, to our surprise, was that if here is the amount of gas bubbles that we measured in this experimental setup, we did exercise 30 minutes before we dive the animals, 5 hours, 10 hours, 24 hours, and 48 hours. And you see, it's only 24 hours who had a dramatic effect. And the effect was so dramatic that actually the controlled experiments was an experiment that killed absolutely all animals. 100% of the animals were killed by that kind of decompression. And we opened the gas bubbles everywhere. We do one bout of exercise. In these animals, 90 minutes of exercise, 24 hours before we did the dive. And as you can see, there are hardly any bubbles there. And you open the animals up, and there's nothing there. So this was then a dramatic way to show that actually this simple thing removed all gas bubbles, which came as a total surprise to us. We had never expected this, and I guess that if we had asked for money for an experiment to demonstrate that, not one agent in the world would have given us 5 cents, and no one would have believed us. Well, we did it, and here it is. And we've done this in man, which is that exercise on the dive prior to 24 hours before we dive them. It's been published in a very reputable journal. Even if you don't know much about diving, you can, or bubbles, you see that these light points here, these bright spots, they are gas bubbles, dramatic, quite a lot of gas bubbles for this dive, which is a dive for 18 meters for 80 minutes, US Navy procedure. And then we do one single bubble exercise, there is nothing. So it works also in man, not only in rats, but also in man. And we've done repeatedly this again, so there's no doubt about it. This mechanism also, what we don't know for 100% sure is this mean that this dive is completely safe. We have some indications that yes, it may be a safe dive, but we haven't documented that properly yet. And why? What's happening? Well, what we have done is that we have shown in a number of experiments that something called nitric oxide, which is a gas that is produced in blood vessels in the brain, and some very important messenger, and is the most important drug that is produced, and it's responsible for the widening of the blood vessels when you do exercise. And this particular drug, we thought in theory that this must be related to this particular phenomenon, because one of the things that this drug also does, or this stuff does, is that it changes the surface property of the endothelium. If you remember the slide I showed you, where Harvey had said that the point of instability, which means that we believe that what's happening here is the precursors that are formed on the vessel wall, they are, by giving this NO, they are removed and there are no precursors to grow from. We think that's the mechanism. We've blocked NO, we've given NO to animals, and we've shown that that is responsible, partly responsible for this phenomenon. And we have demonstrated that nitric oxide is responsible for this particular phenomenon, that gas bubbles disappear. And this is so important because the NO is the most important substance for having proper endothelial function. And endothelial dysfunction is the basis of cardiovascular disease. That is sort of a very important precursor, long-term cardiovascular morbidity and mortality. So this makes the link between diving, the rather esoteric subject of diving, towards more important areas of medical, of medicine, namely cardiovascular problems. So NO is involved here, and we are studying mechanisms that are of importance, and this observation that one single bottle exercise has an effect has spanned a lot of experimental activity, both in animals and in man, showing that exactly the same mechanisms and changes in endothelial function happens after only one bottle exercise. So one of the effects of exercise, the regular exercise, is that it is the single bounce that actually makes the difference. It's the importance of one single bottle exercise, and that has dramatic effects. We've also done it in man again. We're giving the nitroglycerin to man, and we're giving it to animals. And we've shown that this is from one particular dive, 18 meters, 80 minutes in a chamber dive. And this is 30 minutes, 30 meters, 30 minutes in water, swimming in water. And you see in both of them there is a significant reduction in bubble formation in both of the both conditions. So it works also here. So the nitroglycerin or nitric oxide is involved in the process clearly. And we can demonstrate. That means, of course, that we actually are getting to the point that we have also shown in other animals, like a pig, we have demonstrated exactly the same effect. So actually this raises the interesting possibility that decompression sickness or bubble formation, which is the basis of the serious symptoms we believe, they can't be eliminated by a drug. To make this a bit more interesting than nitroglycerin, we've heard people who have angina and prolapse. This is also the main substance that is responsible for the effect of Viagra. So no guys, Viagra is the thing if you want to go diving. Good news. But it's not the only mechanism. We have shown that also other mechanisms are involved, something called heat shock protein. Heat shock protein is a set of proteins that are developed as a response to protect you against injury. You can demonstrate it very easily here. This is this so-called heat shock response. It's called heat shock because it was demonstrated the first time with heat, but it's also responsible for changes that you can see in. It's also responsible for. It can also be caused by hypoxia, hyperhypoxia, ischemia, some toxic substances. It's a generalized response, protective response. And this is sort of demonstrates what it does. If you have a group of cells and you expose them to 46 degrees, in this experiment you see that all the cells die. If you then, however, at a certain time before this heat exposure happens, expose them to a lower heat or a lower stress at a certain time, a certain dose, at a certain time before you do the real experiment, you see all the cells survive. So this is the basis of something we've called the good stress, actually, that are stressors that actually makes you more resistant to injury and actually can promote your health, which is very important. And the reason I mention this is because in diving, which is a small field, and diving research is a very, very small field, it's important to find these kind of connections because that makes your activity interesting for a lot of other subjects. We also tested that in rats that we had heated them to 42 degrees for 15 minutes before 20 hours, 24 hours before we performed the dive. And we've shown them, for some theoretical reason, we believe that would lead to less bubble formation. It did not. It produced just as much bubbles. However, the mortality went down by 50%. This is the mortality in the animals. All animals in the controls die. Only 50% die in the exposed group. So actually, going to the sauna, that is one stress. There are many other stressors. It seems that these stressors also are able to protect you. So this is another mechanism that actually can protect you on the effect of these gas bubbles once they're formed. I mean, we are still looking. And this is just to demonstrate that actually what I'm telling is not just one of these heat shock proteins. This is the endothelial wall. This is the control experiment. And here you see this nice, in this immunostaining, see this nice green color. That's a lot of this particular substance. So this substance is produced, and probably the substance that is the PET is responsible for this reduction in mortality. We're all talking about the importance of exercise. This is from one particular paper. I reanalyzed, if you go back and analyze and look at the paper, I got the raw data from the author and I reanalyzed it. This is the amount of gas bubbles that you have detected in these experiments. They had two, you can divide it into two groups, one with average VO2 max, oxygen uptake, one with good oxygen, more than or 46 milliliters per kilo per minute or above. And there's a significant reduction in the bubbles that were detected. And we believe that the mechanism here is that good exercise capacity, this kind of exercise, can, if you're not very young, this will be something that can only be achieved by regular aerobic exercise. So you need to do regular aerobic exercise to have this kind of reduction, and we think that's the key. And that this could also perhaps help us to understand why it is the idea that divers who are older, they seem to be more susceptible to decompression problems. This could be one of the mechanisms that endothelial function goes down as you're older if you do not keep up your exercise training. So exercise seems to be very important to not only for general getting out of a problem and be able to swim against the current, but actually to prevent decompression sickness. And of course this is a picture that's taken from a conference of sports physiologists, believe it or not. And once you've seen this, go next time you go anywhere, supermarket, anywhere, and look, and you'll see it looks like that. No one is here, everybody is here, even going down. So, well, we're also working on more conventional ways of trying to prevent the problems, namely trying to develop decompression procedures or decompression models that can be used for more conventional decompression procedures. And the way to do it is, of course, that we want mathematical models, and we are in love with the more complicated the models, the better we like it. And the more mathematics we can put in, the happier we are. This shows the development over time of the classic decompression models that was developed by Haldane in 1905. And this is then the Haldane, this is the number of half-time tissues. And as you can see, the number of, and this is the times, it goes from 5 minutes to 75 minutes in his original model, which had 5 tissues. And then you come up to Buhlmann, who has 16. As time progresses, you can see it moves toward more and more complicated models. And one of the things that everyone who's worked with models will say when you see this, they just, okay, this means that as times go by, these models get less and less observable. And the meaning of that is that you can, when you have a very complicated model, you can, by manipulating the factors or the different parameters and variables in this model, you get nearly any result you want. So what's happening here is that you're actually adapting. You found out that in order to describe reality, you had to have more and more complicated models. The problem there is that this means that the models get less and less observable unless you follow some simple rules. Now, what is a model? Well, according to the Wikipedia, it is an abstract representation of an object or a system. No, this is good. And I want to stress this, that a mathematical model is a model that's described in mathematical language, which describes the behavior of the system. And it's widely used in many, many fields, and in biology, to describe how a system behaves. Now, the decompression models used today are really not really models, they're more algorithms. And that comes already from after Haldane's times, where they actually more and more went away from describing what's actually happening in the system towards the description of making the model fits the facts. And the most extreme example of that is, of course, the probabilistic models that do not care at all of the underlying physiology. They're just saying we have an outcome, which is the decompression sickness, and then we fit the model to that outcome. If that gives, for instance, totally meaningless values of perfusion or diffusion or anything you have, that's not really important. What's important is to fit it to the data. And the decompression models, just to make it very simple, we have the Haldanian principle, which is the, as Bruce told you here yesterday, there are models that describe the supersaturation models, and then you have the bubble models, and I put them in brackets because these models are bubble models, but the basis is supersaturation. As saying when you reach a certain level of supersaturation, bubble starts to form. You have a different class of models, but the main point here is that these models describe bubble formation, but they're tested using reported decompression sickness as an endpoint. So you're dependent on right reporting, right diagnosis, cultural factors, psychological factors. There are a lot of factors that influence the diagnosis of decompression sickness, unless you keel over with a very serious symptom, neurological symptom. But in most cases, that's not the case. And decompression sickness is getting to be a rare disease. And the problem then, of course, is how do you evaluate the model? Well, there are other group of models that describe decompression severity, stress. One of them is the model made by Gernhardt, which is the base for Orton-Ehring's procedures. And Mike Gernhardt is now head of the development of decompression procedures in NASA for EVA activity. And there is another model made by a Turkish guy called population balance model, which simply is the same type of model that you use to describe, for instance, the herd of deer. And the herd of deer grows as long as there is enough grass. When the grass starts to get scarce, the population goes down, to make it very simple. And the same thing you have in bubbles, because they grow from a certain nuclei. There is a population of nuclei. There are big nuclei, there are smaller nuclei. So that's a different type of model. But The problem with this approach is that there are no established methods to calculate profiles from these models, and there are also no effort into validating the endpoint. So we've tried, before you say that, I'm going to give you an analogy to show you what I feel about models and reality. This is the Ptolemaic view of the world until the 1500s, and for the Catholic Church it was until 1990 or something like that. It was the view of the world. Well, the reason and where the world was, Earth was in the center, and all the heavenly objects went in circles around it. In circles, that's the point. And then Copernicus came along and said, no, I don't believe that doesn't fit all the facts. In truth, the sun is in the middle, and the planets, including Earth, is going around it. And that, of course, costs some of the people who adhered to this last idea. They were burnt on the stake. And you might also know that Galileo, who then used his telescope to actually observe the heavenly object and had the same idea, he had to renounce his book was burned and renounced. And the reason I said 1990 is that this happened in 1640, where the Pope denounced the book. And in 1992, the Catholic Church finally said that no, Galileo might have been right after all. That's 500 years. So I expect they're coming up with new ideas here, right? So dangerous stuff. But the point is that based on that wrong model that we know now as wrong model, they were able to calculate navigational tables that sent people all over the world. We were able to maneuver, we were able to go with the wrong model. They were able to develop tools that allowed them to go all over the known world and also part of the unknown world. However, if we use the analogy and go into space, that model will not longer work. You can't work with that model once you are in a new environment. And my argument is that we need better models if we're going to try to describe reality better, if we're going to go into space. Like, for instance, we've heard about stuff here, but this is all the world record dive. 9 different gas mixes, 11 hours of decompression, 380 meters. This is only outer space of diving. This type of diving, and we've heard about it, rebreathers, all the kind of new equipment, then this kind of models that are not right will probably fail us. That's my hypothesis. We're trying to do something about that, and we developed a model that we call Copernicus because of this analogy, this idea we have. This is then, hopefully, if we manage to get it into production at some point in time, going to be the basis for the new Uvatech computer at some point in time. But the problem I'll tell you what we have done with this Copernicus. It consists of the model itself, which is a descriptive model of the mechanisms behind the occurrence of serious decompression cycle, evolution of vascular bubbles. That is the basis for the model. And also very importantly, we have a control algorithm that calculates a procedure that gives the optimal decompression strategy based on a set of predictions, or a set we said this kind of level of gas bubble formation is what we allow. This is then the procedure that will reach that. And we have a validation strategy that is based not on symptoms, but based on vascular bubble measurements. That is our golden standard. And they have 2 distinct applications. We can use it as a simulation to compare and evaluate procedures and log dives. And we can use it, of course, as based on the bubbles, the risks that we can calculate the threshold for optimal decompression schedule. And we have also worked on methods showing that if you use vascular bubbles that you can measure using ultrasound, that is a very sensitive indicator of the risk of decompression problems. And we're using a technique based on Bayesian statistics showing that that is actually the case. That's in print now, that's a particular study. So actually we have the tools to actually do this. First of all, it's a physiological model. We're trying to describe the mechanisms as good as we can. And you can see we have a number of things that we consider. And we're developing an individually adapted model. At present, these are the things that we take into consideration. However, as we get more data, and we get new knowledge, if we get more data, we can add things down here. So it's open-ended in that sense. And we have calibrated, we have analyzed it using the best data of ultrasound that we have, and that is from the group in Toronto. I just want to make a point about ultrasonic measurements, because that's not easy. I mean, everybody can do it, but analyzing it is a very difficult task. And as far as I know, there are only 2 groups in the world who's ever tried to analyze the method of detecting gas bubbles using ultrasound. And one is the group in Toronto, the other group is our group. And we have analyzed actually how good are we. And the point is, Nishi has shown that if you're not very good, your data are very inaccurate. So even if it's published in all kinds of journals, don't necessarily believe it. It can be true, but it can also, that's a difficult task. However, we used some of Nishi's data that we got from him, and this is then what the model, now this is what we measure, the number of bubbles that we measure. This is the prediction, and you can see this is the line of unity, and you see that most of these numbers are down here, which is comforting because that tells us that the model, our decompression model, is actually more conservative than what can be observed, which is what we want. And you see that a few points are up here are from observations where we have very few observations. So it looks like, at least for this data set, quite hard data. And then I won't go into this, but this shows the optimization procedure. We are able to optimize so that we say this is the optimal point. This is the point that we give the lowest production of gas given the criteria that we have in this model. So we have this optimization techniques. We can make a table now that is giving us the optimal result. However, when I'm saying that, is one of the advantages of using our approach is that you can prove it. And this is then the US Navy a dive. I won't go into the detail, but the point is that this is a dive lasting for about half an hour, a little more than half an hour, I think. US Navy table, and this is the Copernicus table, the red one. You see, yes, many of the decompression models based on bubbles like this, and everybody comes out with this kind of hills, everybody. Any decompression model based on bubble dynamics will have deeper stops. It's a given. And you see, this too. We tested that in experimental situations. This is the experiment using the US Navy profile. This is the amount of bubbles formed. You see, this is something in the order of in this unit, is something in the order of close to 0.4. In units, you don't have to take. And this is what happens when you do the something like 50% amount of bubble formation using the Copernicus model. We found the same thing in a study that Bruce Wink and I did together some years back, where we looked at the surface decompression profile, the in-water phase of the surface decompression profile. But this is the US Navy procedure. This is another procedure that takes exactly the same time to reach the surface, but has a totally different shape. And another one that is much faster. In truth, it is 50% faster than this one. And these are the results. There are an amount of bubbles on this axis. See, that's the amount that's produced by the US Navy table. This is the amount of gas that's produced by this one. Now, this is not quite true, because if you then do the rest of this, which is 68 minutes of surface decompression breathing oxygen following this, you find that this is doing much better than that. But I'm just looking at gas formation in this phase. But you see here that with the 90 minutes bottom time, this actually is much, much better, produce much less bubbles. And interestingly enough, if you increase the bottom time with 50% up to 135 minutes, you see that you're still, compared to this, significantly better, which is counterintuitive. You wouldn't have thought when you looked at this that actually going faster makes it better. And this is sort of introduction of the deep stops, if you want. I mean, this is one way to do deep stops. And we have more data, we have more experimental data showing that this particular trick works. However, and that's very interesting, this is then another simulation with our model. 30-meter dive, with a 65-meter dive, with a longer bottom time, with a shorter bottom time. This is the amount of gas bubbles that we measured, and this is what the computer simulates our model, which you see fits very well. Full of optimism, we then went on, and this is very new. You're getting data that is hardly done yet. But these are the results. This is then the original procedure. This is then the US Navy, the Copernicus procedure. And you can see this is the disregarded. This is an error that I didn't quite have time to remove from the raw data. But that's this. This is disregard that. That's an error. That has nothing to do with it really. You see here, these are the bubbles that we observed on the Bugman profile, and these then are the bubbles that we observed from this rather long dive observed from the Copernicus one. So it fits very well. However, these are the results from the short dive, which you see there are very small differences in these two profiles. There's not a very big difference. But these are the dramatic results. These are the results from the original Bugman one, and this is the supposedly better. So it wasn't better. It was actually worse. And this shows an advantage of this particular testing method. And now we suddenly did something that is a vector test for a model. We showed that it's wrong. We showed where we were wrong. And one tentative conclusion that we can draw from that is that dives with longer than 30 minutes, all very, very tentative. 30 minutes bottom time, they benefit from deep stops. However, the shorter dives will not benefit. They will not benefit. On the contrary, it would be worse if you have the deep stops. So the short dives behave, the supersaturation model described that type of dive, where the point is to set up as large a gradient as possible to eliminate gas. We haven't explored this fully, but I'm just showing you this to show this approach, how it's not possible. By using this kind of approach, we can say, okay, the model we originally set up is not a correct description of what's actually going on. And we can go on, and as we are doing now, we're trying to modify the model to take this into consideration. This, of course, is something that I wrote in 1995. I stole it from Stephen Hawking, perhaps the most prominent astrophysicist in the world, who has now the professorship in Cambridge that Newton once had. And he had a lecture in 1980. And I said, to be very ambitious, this is the possibility that the goal of decompression research might be achieved in the not too distant future, say by the end of this century. By this I mean that we might have a complete, consistent and unified theory of the physical and physiological interactions that would describe all possible observations. When Hawking was hunting for a unified theory of describe everything from from atoms to the universe. Later, Hawking has said that he doesn't believe that that is possible. So I don't know. But we are looking for a unified, we want to have a theory that would explain as much as possible of what we can actually observe, and we're going to explain it with hard data. So I have to admit, as Faraday, a very much more famous man than he said, I may be largely wrong, I'm free to admit, we can be right altogether in physical, even less, which is essentially progressive and correct.